Here's the solution to problem number 3. So if I look at this, I'm looking for the pressure at the bottom of the tank when it's closed off. So I've got a little water tank, or big water tank, and it's got a vent at the top. It's so big at the top that the water's not moving downwards at any speed, so the velocity is going to be 0, and since it's vented to the atmosphere, the pressure is going to be 1 atmosphere of pressure. So the height at the bottom is equal to the pressure of everything above it, above the bottom that is. So that's rho gh for the fluid plus the atmospheric pressure above it. So if I start by organizing my thoughts by listing my givens, I know the pressure at the top is 100,000, it says atmospheres, but that should be pascals. So 100,000 pascals, and the depth of a height is going to be 15 meters. So the pressure at the valve is equal to the pressure of everything above it. So the pressure at the valve is equal to the pressure at the top plus rho gh. The pressure at the valve is 100,000 plus all the other math stuff that's in there. And that gives me the pressure at the valve to be 247,000 pascals. Okay, so that's great. So the valve's not open. But what's the pressure when the valve is open? But once it's open, on the left side of the valve, the pressure is still this 241,000 pascals. So we're assuming it's not really moving at that point. But once I pass that point and expose it to the atmosphere, the pressure is 1 atmosphere of pressure. So once I get outside, it's 1 atmosphere of pressure. No math, it's just a concept you're looking at. Okay, let's go on and look at number C. Assuming the effective cross-section area of the valve opening is 2 times 10 to the negative second meters, a small valve opening, find the flow rate. So flow rate is volume over time, which is also area times velocity. So I'm going to use this idea of area and velocity because I know I can figure out the velocity that's coming out, and I know they gave me the area. So I can figure out the velocity, not using the continuity equation with the conservation of mass, but with using conservation of energy. And I know that because I have this potential energy at the top, and I have this kinetic energy at the bottom. And I have this height. Let's see, how can I say this? I'm trading height for speed in this problem. So when I look at this, the pressure at the top is going to be 1 atmosphere of pressure. The pressure at the bottom is also 1 atmosphere of pressure, so they're going to divide out. And at the top, I'm assuming that the top of it is really big compared to the size opening, so it's not going to be moving very fast, or not moving at all. And then at the bottom, well, that's the lowest height, so I'm not going to have any gravitational potential energy. So what this all sets up to be is just the potential energy per unit volume at the top is equal to the kinetic energy per unit volume at the valve. So rho gh equal to 1/2 rho v squared. The rho's cancel out, and then solving for v, I get v is equal to the square root of 2gh. But I'm not done. The question is to find the flow rate. So now I'm looking at the flow rate, which is defined as that area times velocity. So I'll take area times v. So my formula now for the flow rate is A is equal to the square root of 2gh. Putting in my numbers, I get a final answer of 0.741 meters cubed per second.